In this video, we'll be going over the SPICE kernels and JSON catalogs required to include instrument observation marks on planetary bodies. So on the left here is an example of Europa Clipper spacecraft doing a flyby of Europa, and on the right are 2D and 3D visualizations of the ground tracks of a sun synchronous orbit around Earth. Here's an Earth orbiting satellite doing a pass of the Nabla Zero Labs office in South Pasadena, California, where the satellite is pointing its instrument nadir. And here are all the 45 flybys of Europa from the published Europa Clipper tour trajectory. We'll be starting out by going over the new observation catalog for the Nabla Zero Labs pass scene. So we start with defining this object as class observation, set its name, start time, and center, like everything else that we do. Define its trajectory frame to be the Earth's body fixed frame, since the observations are with respect to the Earth's surface, and same with the body frame. Then we get to geometry, where this is of type observations. Its sensor is the name that we give the spacecraft instrument in the spacecraft catalog. And the rest is for the appearance of the footprints, like opacity, color. Higher side divisions makes footprints look more circular, just like with instrument frustums. And fill-in observations is for whether the marks should be outlines or filled-in shapes. And groups are for when the observations should be making footprints based on where the instrument is pointing. And in this scene, we only have one, but in the Europa Clipper one, we'll see that we need many separate groups. And observate is how many seconds in between creating a footprint. Once the observation catalog is made, you'll need to add it to the load catalog, and everything else will be the same as in the previous video. And as a quick note, you can define points on Earth's surface in a catalog instead of creating a BSP kernel for them, and here we included the Nabla Zero Labs in the spacecraft catalog, where we define its trajectory frame as Earth body fixed, and its trajectory to be fixed defined by spherical coordinates, where here they mean latitudinal coordinates, so latitude and longitude coordinates are plugged in as you are used to seeing, where 0 degrees latitude is on the equator. And for the Python script, everything is the same, except here we need to make sure we call show object on spacecraft observations, since that's the name that we gave it in the observations catalog, and then also show Nabla Zero Labs. Next up is the Earth covered scene, where here the observations catalog is the same, except we extend the time to a day and set the obs rate to a much higher value and increase the reference angle in the instrument catalog. And we do this because Cosmographia will slow down a lot if you have too many points of observation. So in order to compensate for that, we use less points but a larger reference angle to make up for that lost area. Also, the reference angle we use for the Nabla Zero Labs pass scene is way too small when we zoom out to this scene. So we would need to increase the reference angle anyways in order to actually be able to see the observations. And in this scene, instead of rotating the camera around the Earth, we just set the camera to the inertial frame and allow the Earth to rotate underneath it. This is the Europa flyby scene, where here we define the spacecraft body reference frame the same as we do as the rotating reference frames with the text dynamic frame kernel instead of the binary attitude quaternion kernel, since this orientation is going to be constant in the scene, but either way works. And the instrument kernel is defined the same as usual. And for the observations kernel, again, it's the same as before, except here we need to make sure we precisely set the time of the flyby and the desired observation rate. The Europa covered scene is a bit of a challenge since there are 45 flybys and they're all coming in at different angles. So here's a plot of all those flybys ground tracks, and this was made by finding the ephemeris times of the closest approaches to Europa, which are shown in the purple points with the plot here on the right, and then getting the spacecraft position vectors with respect to Europa from 10 minutes before and 10 minutes after the flyby in the IAU Europa body fixed reference frame, and then converting those position vectors to latitudinal coordinates. And Europa's surface image can be found in the textures directory within Cosmographia. So it's Cosmographia, cosmographia.app, contents, resources, data, textures, where a lot of them are .dds images, but those can easily be converted to a .png and plugged into matplotlib and Python. The observation catalog is a lot longer since we have to implement all 45 flybys in the groups variable, and this was also done within the same Python script of finding all the flybys, converting the ephemeris times 10 minutes before and 10 minutes after to a calendar date, writing all the statements here to a file, and then copying and pasting them into this catalog. So I wouldn't recommend doing this by hand because it's just too many of them. And also the observation catalog allows for discrete number of altitudes to be represented by user-defined colors. So that's it for this video, and in the next one we'll be showing how to create engine plumes using the particle systems functionality in Cosmographia.